Welcome to this explainer. Okay, right now, as you're taking this in, your feet are probably planted firmly on the floor. Or maybe you're sitting down, held snugly against a chair cushion. We take it for granted literally every single day, but the force keeping you tethered to the earth right this very second is actually one of the most fascinating phenomena in the entire universe. So today, we're unpacking the history of gravity. It all starts with an incredibly simple yet profoundly difficult question. Why do things fall? I mean, it seems super obvious to us now, right? But gravity is essentially the ultimate scientific cold case. Brilliant minds have spent over 2,000 years trying to crack this exact mystery. And the journey to our current understanding is it's absolutely mind-bending. Here is our roadmap for today. We are going to cover 1. Aristotle and natural places. 2. Galileo questions the rules. 3. Newton makes gravity universal. 4. Einstein bends spacetime. 5. The quantum gravity quest. And finally, 6. Modern mysteries. Let's dive right in. Starting with Section 1, Aristotle and natural places. To really understand how we started, we have to go all the way back to the ancient Greek philosopher Aristotle. He gave us one of the earliest, most comprehensive scientific explanations for gravity. As you watch this animation unfold, you'll see he proposed a highly intuitive, geocentric model of the universe based on concentric spheres. Notice how Earth sinks in water, water sinks in air, and flames naturally rise above the air. Why does that happen? Well, according to Aristotle, everything just gravitates toward its natural place. He thought the center of the Earth was the center of the universe, so heavy things naturally wanted to go there. Honestly, it's remarkably consistent with our basic everyday observations. And crucially, he believed heavy objects fall proportionally faster than lighter ones, meaning a heavy metal rock should fall faster than a piece of wood. Makes perfect sense, right? Well, check out this timeline. Look at that massive 2,000-year gap. We start way back around 350 BCE with Aristotle's natural place, and then total silence. There was this enormous span of human history where Aristotle's ideas went almost completely unquestioned. It wasn't until around 1600 CE with Galileo, then 1687 with Newton, and 1915 with Einstein that we finally see these rapid-fire modern paradigm shifts. So what actually broke that 2,000-year silence? That brings us to Section 2. Galileo questions the rules. Enter Galileo Galilei. He was the guy who finally challenged the long-standing dogma that heavy things fall faster than light things. But hey, quick mythbuster first. As fun as it is to imagine him dodging Taurus while chucking things off the Leaning Tower of Pisa, yeah, that's a total myth. What he actually did was conduct highly controlled empirical experiments, rolling objects of different weights down inclined planes. And through this, he found they actually fell with the exact same rate of acceleration, entirely regardless of their weight. But here's the thing, Galileo didn't just rely on physical experiments. He was an absolute master of theoretical logic. Modern philosopher Daniel Dennett hits the nail on the head in his book Intuition Pumps, saying, "Some thought experiments are analyzable as rigorous arguments, in which one takes one's opponent's premises and derives a formal contradiction." This quote perfectly sets up Galileo's brilliant theoretical thought experiment, the reductio ad absurdum. He completely dismantled Aristotle's 2,000-year-old premise using literally nothing but pure logic. Let's step through this contradiction and watch how this logic builds on screen. Step 1. Let's just assume Aristotle is right, and a heavy stone, we'll call it A, falls faster than a light stone, B. Okay, step 2. What happens if we tie them together? Well, since stone B is naturally slower, it should create drag, slowing stone A down. But wait, look at step 3. Tied together, stone A and stone B combine to create an object that is heavier than stone A alone. Therefore, according to Aristotle's own rules, the combined stones absolutely must fall faster than stone A by itself. Do you see the trap here? Galileo proved that tying the stones together would create something that falls both faster and slower than the heavy stone alone. It's a total contradiction. This definitively proved that acceleration must be the same regardless of weight. Just brilliant. Moving on to Section 3, Newton makes gravity universal. Building on the work of Galileo and embracing the Copernican principle developed by Nicholas Copernicus, Sir Isaac Newton created an absolute breakthrough. He realized that Earth's falling motion is the exact same behavior that holds the moon in place. Before Newton, people didn't think the rules governing a rock falling on Earth had anything whatsoever to do with the celestial motion of giant planets in space. But Newton mathematically united them. He proved gravity as an attractive force acting between any two objects with mass. And this system was so robust, so brilliant, it went unchallenged for over 2 centuries. But then we hit section 4, Einstein bends space-time. Now this is where the story completely flips on its head. Looking at this comparison, on the left we have Newton's universe, right? Gravity is a mathematical, invisible pulling force acting across space between 2 objects with mass. But on the right, Albert Einstein's general theory of relativity completely redefines reality. To Einstein, gravity isn't a pulling force at all. Instead, massive objects are literally bending the very fabric of space and time. Let's define exactly what that means. Space-time is the collective fabric of space and time. In this modern understanding, objects simply want to follow the shortest, straightest path possible through that fabric. However, that path gets modified or curved by the warping caused by nearby massive objects. Think of a heavy bowling ball resting on a soft mattress. It creates a deep dip. If you roll a marble nearby, its path naturally curves down into the dip. Not because the heavy ball is pulling it like a magnet, but because the mattress itself is warped. That is exactly what planets and stars do to the fabric of space-time. Which leads us to section 5, the quantum gravity quest. So Einstein's general relativity works wonderfully. It fits the data to an incredible level of precision. But here is where things get super messy. General relativity relies on a smooth, continuous fabric. But that is completely incompatible with quantum physics, which requires energy to be granular and chunky. Now, usually this isn't an issue. Relativity handles the really, really big stuff, and quantum mechanics handles the really, really small stuff. But what happens when you have something incredibly massive squished into something incredibly small? You get a black hole. And right along the boundary of a black hole, these 2 major frameworks of physics clash spectacularly. Enter physicist Stephen Hawking and the concept of Hawking radiation. This is the energy he predicted would radiate from black holes. Hawking theoretically resolved this intense, localized conflict by applying quantum mechanics to the smooth edge of a black hole, predicting it must emit energy. But while this is a brilliant theoretical patch, science still desperately needs a verified, comprehensive theory of quantum gravity, like string theory, for instance, to fully unite these concepts and accurately describe physical reality once and for all. Finally, we reach section 6, modern mysteries. If you thought we had it all figured out by now, no way. The story of gravity is a highly active, living process of discovery, and scientists currently face 2 massive, universe-scale experimental mysteries. First up, dark matter. For our current understanding of gravity to actually apply to the universe, there must be an enormous amount of unseen attractive force helping to hold galaxies together. Second, dark energy. This is an unseen repulsive force that is somehow pushing distant galaxies apart at faster and faster rates. We can't see either of these directly, but we can clearly witness their invisible gravitational effects pushing and pulling on everything around us. These aren't just obscure math problems. They are the literal, unseen scaffolding of the universe you and I live in, reminding us that our model of reality is still very much a work in progress. Which leaves us with a deeply provocative question to ponder. Will we ever find a unified theory of quantum gravity? I mean, from Aristotle's natural places to Galileo's ingenious contradictions, Newton's universal math, and Einstein's dynamic spacetime, every single time we think we've reached the end of the road, a new genius comes along and completely reimagines reality. The puzzle of gravity keeps our feet firmly planted on the ground, for sure, but it also invites us to keep looking up, reminding us just how much of our universe remains beautifully undiscovered. Thank you so much for joining me for this explainer. Keep exploring and never stop questioning the world around you.